All right, welcome. Let's start with these announcements. Homework 6, remember, will be due on Tuesday, and then right at 1 o'clock when you have that submission cutoff is when the solution for homework 6 will be available on Blackboard, and then that'll give you a day to look it over, make sure that you understand all those problems, and then we'll have our exam on Wednesday. I've already posted the formula sheet on Blackboard that I'm going to be printing and making available for you. So you don't need to print it. I'll bring a printed copy. But just in case you wanted to familiarize yourself in advance with that formula sheet, it's there now. And you should bring your computer for the exam. We've been solving a lot of stuff using like iterative methods and Microsoft Excel. And so bring your laptop for the exam, and it's going to be covering through the first lecture of the semester up until today's class. It won't include Monday's class meeting because on Monday we're going to be talking about the design project. And so that kind of gives us a little bit of a buffer space between the last lecture that's included in the midterm and when you take the midterm. So unfortunately, we only have 50 minutes for the test. That means I'm not going to be able to ask you one of every type of question you've had through the semester. You've solved lots of different types of things. So it'll just have to be a sampling. Are there any schedule or announcement questions that you've got before we move on to talking about pumps a little bit more? Wheaton? Excuse me?
We don't have a laptop.
They make them available at the library. You can check them out from the library, and so my suggestion would be to start there. And if the library can't help you, which hasn't been the case, I think, in the past when other students have been checking them out from there, they've always had some. But if they didn't, then let me know, and I can bring you, I've got like an 11-year-old laptop that is still mostly functional, and it could run Excel, and so I'd bring that in. Other questions? All right, so we're going to be talking about what's known as affinity laws today, and then I also have some additional practice prepared for the Nodal method. As I was looking through the assignments that included the Nodal method, it seemed like we could use some additional practice on that. So the affinity laws are ways of understanding how pumps will behave under different conditions than they were originally characterized. And so it can sometimes be the case that a pump manufacturer will make pumps with a similar shape but different diameters. And so here is a picture of two different pumps. If I remember correctly, this is a 3-inch diameter pump and this is a 4-inch diameter pump. And they share a lot of the same internal characteristics, like the number of vanes on the impeller blade is the same, the curvature shape is the same, the material is the same, but the difference is just simply everything's been scaled up on the 4-inch diameter pump. And so it would be normal to expect that they may behave similarly, but that there's also going to be some kind of differences because of the increase in diameter. And so that's an illustration of how, if we knew the characteristics of the 3-inch pump, we might want to be able to predict quantitatively and numerically, without having to do like some physical experimentation, we'd want to be able to extrapolate and understand how the larger 4-inch diameter pump would behave. Or similarly, what if we had a pump and the manufacturer had provided the pump equation for a certain rotational rate, but then it's being operated with what's known as a variable frequency drive. And what a variable frequency drive does is it changes the frequency of electricity. And you may already know that, for example, the power that comes out of electrical sockets here in this building and almost everywhere else is operating at a cycle of 60 hertz, meaning that the plug is alternating between positive and negative charge 60 times in a second. And so that if you plug in a pump, it's going to be expecting that 60 hertz electricity and the alternating current, but a variable frequency drive can adjust the frequency of that cycling, and it's a way to slow down pumps so that they operate at a different speed than their original speed. And so you could decrease the rotational rate of the pump by changing how frequently the electricity is cycling between positive and negative. And so if you did that, if you had a VFD, then you wouldn't necessarily know how the pump is going to behave at a different rotational rate. The manufacturer maybe has only characterized it at a certain rotational speed. So these scaling laws that are shown here on the screen are a way to extrapolate a known pump into different circumstances. And so you can see what each of these variable definitions means. The first of these equations is one we use a lot, because what it will be able to relate is how the flow rate of a pump varies if you're making changes to the rotational speed or the diameter. So for one particular pump, obviously you can't change the diameter of that. That's a fixed physical characteristic. But you can take one pump and rotate it at different speeds. The diameter variable there is just in case there were related pumps and they had similar shape and those same kind of characteristics, but we wanted to know how the known behavior of one of that smaller pumps is being used to predict a larger pump. And so the main thing to keep in mind from this first equation is it's used to predict the ratio of flow rates. And so the 1 and the 2 are just referring to like the pump number 1 and pump number 2. The next formula we don't use as often. It's relating the mass flow rate. And so for both of the examples that we're going to be working through in today's class, we won't use the second equation. But if you had a pump equation that instead of using the volumetric flow rate for the pump, instead used the mass flow rate, then this is the second formula is what you'd use. And actually you may, just by looking, remember that mass flow rate, m dot, is defined as m dot is density times flow rate. And so these first two equations are basically the same, because it's just substituting in the mass flow rate instead of volumetric flow rate. And then if you divide by the density, then that's the same as the volumetric flow rate. So again, these first two are basically just saying if you change the rotational speed n or the pump's diameter, how is its capacity to move flow going to change, whether it's volumetric flow or mass flow. All right. So the rest of these three equations below it relate those similar things. How does changing the rotational speed or the diameter affect the output of the pump in terms of the energy that it's supplying? So not the flow rate, but here H is what we've been writing so far as H sub P, meaning the pump head. Or you can express the amount of work that the pump is doing in terms of the pressure that's being added. So here capital P in this context means the pressure rise, or W dot they mean as the power. So if you were going to be measuring the number of kilowatts of power that's being added by the pump to the system. So the top two equations have to do with the rate of movement of water. The bottom three equations are all about the amount of energy that the pump is adding. All right. So in a normal pump curve, we've got both of those two things in the equation that we call the pump performance curve. We've got the pump head that's being added and the flow rate. So we've seen these pump performance curves before, and remember that to solve for the operating point, we set the performance curve equal to the system curve. So that's been what we've done the last couple of class periods, is just set H sub P equal to H sub P and solve for the flow rate. But here we're doing something different. We're just considering what would happen if we took a pump and we started spinning it twice as fast. And so this given pump head equation that we have is for an 8-inch diameter pump that is used to spinning at 1200 RPM. All right, so ordinarily, if it's spinning at 1200 RPM, then the pump performance curve, let me write this on the board. For N1 is 1200 RPM, D1 is 8 inches, and H1 is 12 minus 0.1 Q1 squared. All right, so first of all, these are just ratios, and so it doesn't matter what units we use. You'll notice that I've defined the variables, but I haven't specified their units. So mass flow rate could be pounds per second. It could be kilograms per day. It doesn't matter. Volumetric flow rate could be CFS, or it could be cubic meters per second. But as long as you are consistent between both, then that's fine. Here I've just used a capital H instead of the lowercase h sub p that we would be using so far, just because H means head, and that's what this is on the left-hand side. And then I've added the subscript 1 just because this is under the initial circumstances. Gordon, could you close the door? Thanks. So any questions so far? Okay, so if we're going to change this to 1200 RPM, then N sub 2 is 2400, and we're sticking with the same diameter, so D sub 2 is still 8 inches, and we want to know what is H sub 2. That is the question. So we'll start with this top equation here, which tells us that this top equation says Q2 divided by N2 times D2 cubed is equal to Q1 divided by N1 times D1 cubed. Now, D1 and D2 are the same. And so we can just eliminate that from the function entirely. So I'm just going to erase that. So all that we're really left with is this ratio of Q2 to N2 and Q1 to N1. So rearranging this, then we could say that Q1 is N1 times Q2 divided by N2. Just rearranging that, and then we can substitute in the actual values that we know. N1 is 1200, N2 is 2400. So Q1 is 0.5 Q2. Okay, now we're going to use this to substitute it in to the changed, we're going to substitute that into the pump performance curve that we were given to find out how does this pump behave under the modified circumstances. So this is just the first half of it. The other relationship that we're going to use is this third equation, which is the ratio of the pump heads to the changes in impeller diameter and rotational rate. Okay, so the other part of it is H sub 2 divided by N sub 2 squared times D sub 2 squared is equal to H sub 1 divided by N sub 1 squared times D sub 1 squared. All right, now again, the diameters are the same, so I'm just going to erase those because diameter on the left, diameter on the right hasn't changed, so we can just eliminate that entirely. And then I'm going to rearrange this so that what we know is H1 is equal to N1 squared times H2 divided by N2 squared. Okay, so substituting in 1200 RPM for N1 squared times H2 divided by 2400 squared what we've got is that H1 is 0.25 H sub 2. Let me bring this up on the screen so far just so that the solution is integrated with the video. Okay, yeah, this is where we're at so far. So what we're going to do is we're going to substitute both of these, the ratio of Q1 and Q2, and the ratio of H1 and H2, into our original formula that's up here at the top. This was telling us the pump performance curve under the first case, and we know the ratio of the first case to the second case, and so we can substitute that in. And so let's just do that. On the left-hand side of the equation, it's going to be 0.25 H2. So here I've just basically taken this expression and put it on the left-hand side of that equation, is equal to 12 minus 0.1 times Q1. So let's put in 0.5 Q2 and square that. All right. So I'm going to divide both sides by 0.25. Since I'm running out of space on the whiteboard, let me just scroll down here on the PDF and show you what the conclusion of this is. Divide both sides by 0.25. So that gives us H2 on the left. And then 48 minus 0.4 times, and then we had inside the parentheses here squared the 0.5 Q squared. So in the end, our new performance curve, this is just the original pump that's being rotated at 2400 RPMs instead of 1200 RPM. It's going to have 48 for the cutoff head and then minus 0.1 Q squared. All right. So it's kind of interesting. That's just a way for us to predict with these affinity laws how the pump's going to behave in a different scenario. So that's the answer to part A. What would be the new performance curve? Any questions on these calculations that we've gone through together? If not, then let's move on to the 10-inch diameter impeller, and we're going to stick with the original motor. Okay, so I'm going to pause for this one, give you some quiet time to solve it, but what we want to find out is using the same top equation and then the middle one. And we have this as our original pump performance curve. So what's changing now is D. So D1 is 8 inches, but D2 is going to be 10 inches. And both N1 and N2 are 1200. So basically follow the same kind of process where you are relating Q1 and Q2. You're relating N1 and N2 for the pump head. The rotational rate's the same. So yeah, let me just pause here for a second, give you a chance to start on these calculations. I'm going to circulate around with the solution, and then we'll take a look at it together. All right, in part B, we're going to take the same motor and match it up to a larger diameter pump. So remember that when you want to move water with electricity, it's a two-part process. The first part of the process is turning electricity into mechanical engineering, and that's what the motor does. and then the motor is matched up to a pump which takes the mechanical energy and turns it into fluid energy. So here we wanted to keep the first part of that equation. We want to keep the motor and just attach it to a larger diameter pump. So it's still spinning at 1200 RPM, but now the larger pump has a diameter for the impeller of 10 inches instead of 8. So rearranging the flow rate relationship tells us that Q1 is 0.512 of Q2. So think about what that means is it's going to be pumping Q1, the flow rate of the first situation is less than the flow rate of the second situation. And it makes sense because it's a larger diameter pump. It's going to be able to move a greater volume of water. So the first situation is just moving a fraction of the flow rate under the second case. Now, as far as the energy that's being added, the same thing is true, that the larger diameter impeller is able to add more head to the system than the first pump could. And so the ratio of heads that's being added is that H1 is 0.64 of H2. So substitute both of those into the original performance curve, which we've done here, and then solve for H2 just by dividing by 0.64 on both sides. And so here is what the new performance curve will look like for that same motor but larger diameter impeller pump. Now the last question this is asking is kind of a concept comprehension check. It's saying if you needed to lift water 30 feet above the source, then what would be best? The original pump, the pump that's being spun at 2400 RPM, or using the same motor but a larger impeller diameter pump. So let's look at 30-foot lifting means that the pump head required is at least 30 feet. Remember that the pump head that you're going to add should be the vertical elevation difference, the delta Z, plus also the friction losses. So the first pump can only lift water 12 feet. So that wouldn't be a good match for what we need to do. The one that we just barely calculated, it's able to add 18 feet of head. So that can do it. It can lift the water 18 feet. And then the other option was the cutoff head for the pump was 48. So either of these modified scenarios will work. But it all just basically comes down to what flow rate would we want to achieve and then how much friction losses are there besides the elevation difference. But what we can rule out is that the original scenario of the 8-inch impeller diameter and 1200 RPM, that wouldn't work because it only has the 12-foot cutoff head. Yeah.
How would the last one we just did work if it only lifted 18 feet?
Oh, sorry. You're absolutely right. It won't work. No, 18 feet won't work. Yeah. Thanks for asking that. No, yeah, it only has 18 feet and 30. I lost track of what it was asking. Yeah, that wouldn't work. So it would only be the one which is adding the 48 feet. Yeah, that's the only one that would work. Got distracted with too many options. Okay. So affinity laws. I think that you have a homework problem that's similar to that. Let's take a look just real quick and see if there's any hidden curveballs that I need to address before you can really jump in on that problem. I don't think so. It's problem 5. So on that homework problem 5, looks like you're given the rotational rate, the impeller diameter, the beginning performance curve, and we're going to use a similar pump that's operating at a different diameter and also a different rotational rate. And so you're going to have to do this process that we just went through of using these affinity laws to find out what does the new performance curve look like. Here's the original performance curve. You need to find the new performance curve and then substitute in the flow rate of 9 CFS to find out how much head is going to be added. So into the new equation that you create, solve for H sub P with a Q of 9 CFS. So I think you've got the tools you need to be able to do that one. All right, so I talked about how we were going to do some additional practice. Let me hand this out. I've printed this problem. What I'd like you to do is solve this one in pairs or in groups of 3. Talk through, before you start substituting in the numbers, talk about the concepts, like just refresh with each other. What's the governing law? I was surprised at how many students reported to me that the head loss would be different through the different routes, because the whole governing law is that the head loss is the same regardless of whether you go through one pipe or the other. Remember the ski resort example where it doesn't matter if you take one path or the other, but the elevation difference is the same when you start at the same point and end at the same point. All right, so pair up, sit with another student, and first of all, before you start solving, talk with them about what the strategy, the problem-solving strategy is, and the equations are on the back side of this in case you need the formula. So nobody should be sitting individually for this one. I'd really like you to pair up and talk over the strategy of this before you start your solving. You two work together? Yeah. All right. Hey, he's a guest visiting. Would you explain to him the underlying principle here of how these problems work?
I will do my absolute best.
That's a good best way to learn is explain it to someone else.
All right. So
Is that who you work with? Why don't you scoot over with this group and you could be a trio. If you put your heads together and are still kind of stumped, I've put a clue on the whiteboard. Just a small clue to get you started.
So it gives us, we have everything we, yeah, we have everything. Because it gives us those, alright, yeah, so your two equations are. If B, will take A is the same as B, times the B by A,
I think he said F is the other.
Kind of, and then you have. Right. A, U, B, U, B equals U, T, and you're, oh, you can plug that in, right, flow rate for B would be. Solve the system, flow rate minus flow rate. So and then flow rate is equal to. Yeah, so B equals that. Okay, and then you just solve for each. Correct. No, you want them in terms of one another. Could you, what we're looking for is intermediate. Or do you, So we just said this equation relating the friction that he gave us. Like because it's over so it's going to snag on the edge. And it's going to zero. So it makes the whole line. Are you using 0.034 about that?
So just at a quick glance, you can kind of get a sense for which pipe is going to carry more flow, because the two pipes have approximately the same length. If you look at B versus C, they're pretty much the same length, but pipe B has a bigger diameter. So same F value, similar length, but pipe B is a lot larger in diameter. And so my suspicion is that's going to be the one that carries more flow. And when we actually do the calculations, actually make the substitution of the F value, the length, diameter, areas, and so on, what we would get is the total flow rate, the combined QB and QC is 0.15 cubic meters per second. But then of those, the pipe B is carrying double the flow of pipe C. So that extra diameter helps a lot. It helps reduce the resistance to flow by quite a lot. So that's why more flow is going through B than C. The second part of this question was to try and find what's the pressure at the node Y. So we know the pressure at X, and then there's also an elevation change that's happening. So node Y is lower. So if there was no pressure, if there was no head loss due to pipe friction, then the pressure at Y would be greater simply because of the elevation difference. So we're going to simultaneously account for the elevation difference and also the head loss. So since we're low on time, let me just show you that. I'll pull that up, give you a moment to have a look at the solution, read through what the process is for that. I'm looking at it, and it looks like I didn't account for the elevation change, did I? Because we go from 112.5 down to 105.65. So I'm going to have to further adjust the pressure because of that. Oh, I've still got 2 minutes. You're not leaving yet. I'm going to fix this example before you go. Yeah. Dr. Yoon's exams are easy.
Whoa. Shots fired. Contractually required to hold for the guy because I work for him.
Yeah. All right. So we can just use the hydrostatic equation to find what is the pressure change due to the elevation difference. And so the pressure at Y, because it's downhill, would increase by 67,000 pascals. But then here, this part, it looks like I was just accounting for the energy loss due to pipe friction. So you have 222.5 kPa because of the energy loss due to pipe friction, but then plus 67 kPa due to the elevation change. So the overall pressure at Y would be the 222.5 plus 67.1, well, 67.2, so that gives us 289.7 kPa. I'm going to fix that in my notes in the PDF, but the point is if you know the elevation difference between X and Y, and you know the head loss due to pipe friction, then you can find the downstream pressure at node Y. All right, it's 150. Many of you have an environmental test to go, ACE, so good luck on that. Otherwise, remember that homework 6 is due on Tuesday. And on Monday, we're going to introduce our project, so definitely be here for Monday. Oh, I'm just going to give everybody attendance for today because I forgot to do it at the beginning of class.